All right, class. So now we're going to move on to the next section. And the next section that we're going to talk about is so far we've gone over the naming of alcohols, we've gone over the physical and one of the chemical properties of alcohols, and now we're going to start talking about how we can make alcohols. And so what I want you to first do is I want you to think about what are the previous reactions that we've gone over in previous chapters to make alcohols. So pause the video and try to come up with the different ways that you already know how to make alcohols. Okay, so welcome back. Hopefully you tried to recall that information, which is really important. And so just to kind of give you a review, um, we can hydrate an alkene. We can do the cis dihydroxylation of an alkene. We can epoxidize and then open that epoxide with water. We can do an SN1 or an SN2 reaction of an alkyl halide with water or hydroxide respectively. So these are all different ways that we can make alcohols from things, and these are all reactions starting from either alkenes or alkyl halides. So right now, what we know is what we know so far from previous is if I want to make an alcohol, right? If I want to make an alcohol, I can make that alcohol from either some reaction involving an alkene or some reaction involving an alkyl halide. So we know that already. And what we're going to go over now is how we can make alcohols from carbonyl compounds. So the first thing to think about is, are carbonyl compounds nucleophilic or electrophilic? And so take a minute and try to think about whether a carbonyl compound. So when we talk about a carbonyl, remember we're talking about compounds with, this is the carbonyl functional group, the CO double bond. And we're going to go over later on in the semester that there are different types of carbonyl compounds. So right now we're just going to focus on the carbonyl itself, and we're going to kind of be introduced to different types of carbon, which you've already gone over, but there are going to be different types of compounds with this CO double bond. So the question here is, the CO double bond nucleophilic or electrophilic? So pause and try to figure that out. Okay, so welcome back. So if we look at the carbonyl compound, the oxygen is more electronegative than the carbon. So the oxygen is partially negative and the carbon is partially positive. So that actually makes the oxygen of the carbonyl nucleophilic, and it makes the carbon of the carbonyl electrophilic. And what that means is that because the carbon of the carbonyl is electrophilic, so again, this is partially positive, this is partially negative. Because the carbon of the carbonyl is electrophilic, what that means is I can probably take this molecule, react it with a good nucleophile. That good nucleophile can do a nucleophilic attack on that electrophilic carbon. So that's the nucleophilic attack arrow, kicking the electrons up. And we can basically make the alkoxide, right? We can make the alkoxide by adding a nucleophile to that carbon. And then if I take that and I react that with acid in a second step, I can protonate the alkoxide to make the alcohol here. So let's go over different ways we can do that. And so before we get into that, I wanted just to kind of go over this idea of what I call the ladder of oxidation. So this is going to be pretty useful for this chapter and for future chapters. And so what I want us to think about is, we're going to be using these terms oxidation and reduction, and I want us to think about what that means. So when I oxidize a compound, what I'm doing is, obviously from general chemistry, you might remember oil rig, right? That's how I taught my Gen Chem students, oil rig, right? For redox reactions, oil rig, where it's oxidation is loss of electrons, reduction is gain of electrons. And in general chemistry, you probably did assigning oxidation numbers and seeing which ones go down and which ones go up, and that determined what was oxidized and reduced. And that's totally doable, and that we can do that. But in organic chemistry, one thing to think about is when I use the term oxidation, where that term comes from is it comes from adding more oxygen to a molecule or making more bonds to oxygen. And then the opposite of oxidation is the reductions, right? So we have the redox reactions. And in reduction, we're making less bonds to oxygen. So if we look at carbon molecules, the most oxidized form of uh, the most oxidized form of carbon is carbon dioxide right here, right? This is the most oxidized form of carbon. This molecule, the carbon's making 4 bonds to oxygen. And we can reduce that molecule, and as we reduce it, what you see is we're starting to make less bonds to oxygen. So this carbon's making 4 bonds to oxygen, or 2 oxygens. This carbon is making 1, 2, 3 bonds to oxygen, so that's an ester or carboxylic acids. Ketones and aldehydes, they're making 2 bonds to oxygens, right? And then alcohols are making 1 bonds to oxygen. And then the alkyl groups or alkanes have no bonds to oxygen. So we can take molecules and reduce them, so we can go from more oxidized to less oxidized by basically making less bonds to oxygen. We can also go up the ladder, and by going up the ladder, we can oxidize these molecules, so we can make more bonds to oxygen. And right now, what we're going to focus on is the reduction part. So going down is what we call reduction. So when I take something and I make less bonds to oxygen, I can reduce the molecule. So what we've seen is that what we're going to see is I can go from here to here or from here to here. And the way you do this is you just basically when I showed on the previous slide, we basically are going to add nucleophiles to this electrophilic carbonyl here. So this carbonyl, all these carbons of these carbonyls are electrophilic. So what we're going to do is we're going to start going over a couple of different compounds that we're going to start going over different reagents that we can use to reduce carbonyl compounds. And the first 2 that we're going to go over are what are known as hydrides, lithium aluminum hydride and sodium borohydride. If you look at these reagents, they're what we call they're not organometallic reagents, they're hydride reagents. And when you look at them, what you see is that you have a hydrogen, a nonmetal bound to a metal. And anytime you have a nonmetal bound to a metal, this atom is more electronegative. So what that means is that this atom right here, right? This atom right here is going to be partially negative. The nonmetal is going to be partially negative, and that's going to be partially positive. Same thing down here. Boron is a metalloid, but it's still going to act like more as a metal versus a nonmetal, partially positive, partially negative. And so what that means is we can think of both of those molecules as equivalent to H minus, and that's what's really important here, right? Both of these compounds are equivalent to H minus. So we make what we call hydride. That's where the name comes from. H minus is hydride, right? And so that H minus we can add to just based on what I showed you on the previous slides of adding the nucleophile to the carbonyl carbon, we can add H minus to these carbons. Now the way this works is the higher up on this ladder you are, the less reactive you are toward nucleophilic addition. So this molecule, the ester, is less reactive than ketones and aldehydes. So to reduce the ester, I have to use the more reactive hydride, H minus. And notice that after I add the H minus, so what's happening here, and we'll do the aldehyde version. So the way this looks is I have H minus, right? That H minus is going to attack the carbonyl carbon, so that's a nucleophilic attack, kick the electrons up. And that is, I'll draw it up here. I will draw this up here like this. That's going to make the alkoxide. So there was already a hydrogen there. Let's just make this, I'll put a square around the hydrogen that I'm adding. So that's adding it. And then when I add the H plus, right? When I add the H plus here, the H plus is going to protonate So if I have H plus here, which is in that next step, that's going to do a proton transfer on the O minus to give you the alcohol here, okay? And lithium aluminum hydride is more reactive than sodium borohydride. So in order to reduce the more reactive ketone and aldehyde, I can use either LAH, lithium aluminum, so LAH is the shorthand notation for lithium aluminum hydride. I can use either LAH followed by acid or sodium borohydride followed by acid. But sodium borohydride, which is less reactive, will not reduce the ester, okay? And we actually just drew the mechanism for the sodium borohydride reacting with the ketone and the aldehyde, so you don't need to do that now. So again, just to go over the mechanism again, what you have here is you have electrophilic carbon that's going to do nucleophilic attack. The hydride H minus will do nucleophilic attack, pushing the electrons up. That makes the alkoxide, which is then protonated, so there's a proton transfer, so O minus attacks the proton here to give you the alcohol. So why don't you take a minute and try to come up with the products of these reactions based on what we just went over. So why don't you pause and take a second to come up with the products of these reactions. All right, so welcome back. So again, what you want to think about when you see these reactions is when you see sodium borohydride or when you see lithium aluminum hydride, you want to immediately think about this as being H minus. And when you see this H minus, you want to immediately think that you're doing a reduction. So these are basically addition reactions between H minus and a carbonyl. That's kind of what a reduction is. So when you see H minus, you immediately want to be thinking about reducing like a CO double bond. And so when you see that H minus, once you've realized that it's H minus, you can think about that attacking the carbonyl, kicking the electrons up. That one attacking the carbonyl and kicking the electrons up. And so when you do that, the final products you're going to get in both cases are going to basically be where that hydrogen, right, where this H minus, and this is why they color it, and this is why when I tell you to make the note cards, coloring them helps, because that's kind of like the mnemonic for you to kind of understand what atom is kind of where the atoms are going, right? So this nucleophilic atom is blue, attacking that carbon, and that's that new bond you're making. And notice that when you react an aldehyde with sodium borohydride, you make a primary alcohol. This carbon's only bound to one other carbon. And when you take H minus sodium borohydride and you react it with the ketone, you make a secondary alcohol here. So again, just like we went over, in order to reduce carboxylic acids and esters, sodium borohydride is not reactive enough, so we have to use the more reactive LAH. So in LAH, what happens here in both of these cases, you add multiple equivalents of H minus. So again, the tip-off here that you're doing a reduction, is that you see lithium aluminum hydride, which is the H minus. That H minus is going to add to the carbonyl carbon here. So H minus adding to the carbonyl carbon. And when you see LAH, what you want to think about doing is you want whatever carbonyl carbon you're adding to, that carbon is going to you're going to basically replace, you're going to add an OH, right? That carbonyl carbon is going to have an OH attached to it, and then as many hydrogens as you can attach to it while not breaking the carbon-carbon bond. I hope that kind of made sense. But I'm trying to get you to see and understand, recognize when you're supposed to be doing these reduction reactions. So let's look at the mechanism of the ester reduction really quickly. And so in the ester reduction, what happens here is when I see my LAH, right, I'm thinking of that as H minus. That H minus is going to add to the carbonyl carbon here, pushing the electrons up. So I'm going to draw this now in the line drawing structure, like this. So that's the O minus. I still have this OCH3 here, and this is where things get a little interesting. I'm going to go ahead and put a square around the hydrogen that I added. What happens here is that this oxygen, this methoxy group, remember this is called a methoxy group, methyl to methoxy. This methoxy group will end up leaving, and that leaving is helped by this O minus kicking down. This looks a lot like the activating ability of an oxygen on an aromatic ring. So this oxygen will kick down, kick out the methoxy group, and what that gives you is that gives you an aldehyde here, right? And then that aldehyde can be attacked by another equivalent of H minus to give you the alkoxide. So notice that the reaction goes to the aldehyde, and the same type of thing happens up here too. It's the same mechanism. This one minor step in the carboxylic acid, though, is that you deprotonate first before you do these steps. So now I've made my alkoxide, and so now this is the second step. So the alkoxide will be protonated by H plus to give you your alcohol here. Now notice that when you have the 4 hydrogens here, LAH and sodium borohydride, so LAH and sodium borohydride, they have 4 equivalents of H minus on them, okay? They have 4 equivalents of H minus on them. So they can add 4, so for every 1 molecule of LAH or sodium borohydride, those molecules can add 4 times. All right, so now we had gone over the Grignard reagent, and this is where the usefulness of the Grignard reagent comes into play. So we've just gone over H minus. When you make the Grignard reagent, remember, so just as a review, you can take an alkyl, you can take any kind of like alkyl halide or aryl halide. So when I say aryl halide, what that means is an aryl halide is something where you have a halogen attached to a benzene ring, or a vanillic halide, which is a halogen attached to a double bond. You react them with magnesium. The magnesium inserts in between the carbon and the halogen, making this carbon partially negative. And so basically what we have here is C minus, a carbanion. So what that means is I can take the Grignard reagent, and that R minus can add to the electrophilic carbon here, right? So what we can do here is when I see the Grignard, so when I see this, I automatically want to think of the Grignard reagent, right, as R minus, right? So this is nucleophilic, so I'm going to do a nucleophilic, and one of the things to keep in mind is like when I see that I have a nucleophile, I'm looking to do a nucleophilic attack at some point in the mechanism, okay? So I do the nucleophilic attack, that kicks the electrons up onto the oxygen. This looks a lot like the hydride mechanism. The only difference here is that instead of H minus adding, we're adding R minus here. Okay, so that's the R group, and then the second step is the proton transfer here. So you do the proton transfer, and then that gives you the product here. And then this is the byproduct of what you make from the Grignard reaction. And again, we go over this a lot, that there's the byproduct, but we don't necessarily think about the byproduct a lot of times. All right, so why don't you take a minute and try to come up with the products of these Grignard reagents reacting with these different carbonyl compounds. So the goal here, again, and I'll kind of help you with the first one here, is when I see a Grignard reagent, like so when I see the Grignard reagent right here, I don't want to think of it like this. Whatever the magnesium is bound to, I want to think of that carbon as being a carbanion. That's my nucleophile. So I'm trying to figure out what that's going to attach to. So that's going to attach to that carbon there, pushing the electrons up on there like that. Okay? So why don't you take a couple of minutes or more than a couple of minutes, so pause the video, try to come up with the products of all of these reactions. All right, so welcome back. So hopefully you were able to come up with these products. So here, again, what we're seeing here is that this carbon, right, is connecting to this carbon, and then this becomes OH, right? That's the kind of memorization if you want to do more straight memorization. So if you recognize that this is a reduction using a Grignard reagent, that this carbon attaches this to carbon, OH. This carbon attaches to this carbon, OH. This carbon attaches to this carbon, OH. Now, one of the things to also keep in mind is that Grignard reagents are also reactive enough to react with esters. They're not reactive enough to react with carboxylic acids, but they will react with esters. And in terms of esters, this Grignard reagent will add twice. So what happens here is like very analogous to the hydride. So when I see this methyl magnesium bromide, what I want to think about is I want to think about this as being CH3 minus. This CH3 minus is going to add to the carbonyl carbon here, push the electrons up. So I'm going to go 1, 2, 3, 4. So 1, 2, 3, 4, 5. So I have O minus right here. I have my ethoxy group. So this is, remember, from naming of esters, this is called ethoxy. I have my ethoxy group, and then I have my CH3 that was added. And just like in the hydride, the ethoxy group will leave. So this is a leaving group arrow, helped by the O minus, and that O minus, remember, that helping of the O minus is analogous to the phenol being an activator in electrophilic aromatic substitutions. So that's going to then give me the ketone, and then that ketone again will react with another equivalent of CH3 minus. So that CH3 minus will attack that carbonyl carbon, pushing the electrons up here. That gives me the tertiary alkoxide. Getting a little small down here. I don't know why I decided to draw this all like this. And then there is a proton transfer. So now this is all done after step 1. So step 2 is the proton transfer to give me the final product. One of the things that's confusing is even once students recognize that this is a Grignard reagent, one of the questions students have is, well, what's happening with this H3? But why is that H3O plus the second step? And that second step is for this protonation of the alkoxide. So here are the post-lecture questions. So we're starting to get into a lot more reactions, right? And so make sure that you're making note cards, that you're trying to use whatever way you need. And so remember, the way I talk about learning these reactions is you want to be able to look at reagents and starting materials and to be able to recognize what type of reaction is taking place. And then once you know what type of reaction is taking place, that should help you kind of you start off by kind of more memorization with what type of reaction is taking place, and then using the mechanism of those reactions to help cement the actual what happens in all of these reactions. I hope that made sense. Let me know if you have any questions, and I will talk to you later. Thanks. Have a great day.